You sit on your couch, you pull out your phone, tap a button to buy a new blender or a pair of shoes, and you just expect it to appear on your doorstep the very next day.
Right, like magic.
Exactly. But behind that single tap is this invisible choreography, so massive and precise, really. It makes a Swiss watch look simple. So today, we are exploring that exact choreography.
Which is arguably the backbone of the entire modern economy.
Without a doubt. We're doing a deep dive into the design principles of warehouse engineering. We are pulling insights from advanced logistics certification standards, specifically Module 4, Section C, for those following along. We're looking at how facility layouts, space optimization, and performance management actually operate on the ground.
It is an incredibly highly engineered world. I mean, every time you click buy and actually receive a package on time, it is the direct result of the spatial math we're about to discuss.
Yeah, and the stakes are high, right?
Huge. A poorly designed warehouse doesn't just mean like a minor inconvenience for someone. It cascades into delayed shipments, damaged goods, exhausted labor, and just massive operational costs.
Okay, let's unpack this. Because before you can optimize the movement of the boxes, you have to engineer the box itself, right? The physical facility.
Right, you need the actual structure.
Exactly. And as I was going through the source material on facility sizing, I initially pictured warehouse design as this massive game of 3D Tetris, just fitting blocks together perfectly.
Sure, that's how most people see it at first.
But the more I read about how inventory actually moves, I realized it's probably closer to a giant game of Jenga. You have to be able to pull a block out of the middle of the stack without the entire structure collapsing.
That Jenga comparison captures the core constraint of storage density so much better than Tetris.
Wait, really? Why is that?
Because warehouse capacity isn't just about the footprint, the square meters on the ground. It is entirely about the cube.
Yeah.
You have to factor in the vertical space.
Right, because land is expensive.
Spot on. Building up is generally much more economically feasible than building out, especially given the premium on land near major ports or urban distribution centers. I mean, the average warehouse height is around 14 meters now.
14 meters, wow.
Yeah, which allows for just immense cubic capacity.
But that immediately made me wonder about the structural limits. I mean, if building taller is always cheaper than acquiring more land, why stop at 14 meters? Why not just build a 50-story warehouse skyscraper right in the middle of a logistics hub?
Well, the constraints there are strictly physical, and they hit the bottom line really hard. Yeah. First, you have floor slab engineering.
Like the actual concrete on the ground.
Exactly. If you build towering racks holding heavy industrial goods, the concrete floor slab has to be engineered to support these massive, highly concentrated point loads.
Oh, right, because all that weight is just pushing down on a few tiny metal feet.
Exactly. A standard slab will literally crack under the pressure of a 50-story rack system. Then you also need specialized high-reach equipment to access that vertical space.
Which I'm guessing is not cheap.
Not at all. It drives up your capital expenditures immensely. And crucially, going that high exacerbates a phenomenon called honeycombing.
Okay, yeah, the text brought up this concept of honeycombing. And keeping with the Jenga idea, I pictured pulling a block out of the tower and leaving this, unusable gap of empty air behind. Is that essentially what's happening on a macro scale in these facilities?
That is the exact mechanism, yeah. In a warehouse setting, vertical honeycombing occurs when you have a tall column of identical items. So say a single SKU stacked 5 pallets high.
Okay, got it.
If an order comes in and a worker removes the top 2 pallets, you are left with 3 pallets of product and a massive empty gap stretching up to the ceiling.
And you can't just put something else up there.
No, you cannot just slide a completely different product into that empty gap. Because if you do, you bury the original items underneath.
Oh, so making them inaccessible without double handling the new product, you'd have to move the new stuff just to get to the old stuff.
Exactly. So the taller your racks, the more severe this wasted vertical space becomes, because every partially depleted stack represents, thousands of cubic feet of just unutilizable air.
Which perfectly explains a pretty counterintuitive rule in the text. I mean, my baseline assumption was that a facility manager would want a warehouse to be 100% full, right? To maximize that massive real estate investment.
It sounds logical, but it's a disaster in practice.
Right. The industry standard is the 85% rule. The text is definitive. Once storage utilization exceeds 85%, productivity and safety both take a massive nosedive.
Think about the physical mechanics of moving heavy equipment around. If every single slot is filled, You completely lose the ability to maneuver.
You're just totally boxed in.
Exactly. You have no staging areas, no temporary drop zones for incoming freight. At 85%, you have the wiggle room to sort incoming goods and actually execute the labor.
So if you hit 95%.
If you hit 95%, workers end up moving pallets just to get to other pallets. It creates a literal physical gridlock on the floor.
That sounds like a nightmare. So we are intentionally keeping the warehouse at 85% capacity so things can actually move.
Yes, exactly.
But that introduces a completely new physical constraint, which is traffic flow. How do you route a forklift through that remaining 15% of empty space without causing a massive bottleneck?
That is the big question in facility design.
Right, and the text breaks down facility layouts, specifically comparing through-flow and U-flow designs. And honestly, I had this completely backward in my head.
How so?
Well, my intuition said a straight line is the fastest way through a building. You know, trucks drop off at the receiving dock on the left, goods move straight through the storage racks, and they exit out the shipping dock on the right.
A straight line feels efficient in theory, right? It makes sense on paper.
Yeah, exactly.
But in practice, a through-flow layout requires you to basically duplicate your resources.
Oh, because they're on opposite sides.
Right. You need a dedicated receiving team and a dedicated shipping team at completely opposite ends of a massive building. You need 2 separate sets of dock doors, 2 security checkpoints, and 2 staging areas.
Which just eats up costs and space. Whereas the U-flow design forces the goods into a giant U-turn. The receiving and shipping docks are on the exact same wall of the building.
And here's where it gets really interesting. The U-shape solves multiple complex logistical problems simultaneously. First, it allows you to consolidate your dock resources and personnel.
Right, they can share the space.
Exactly. But more importantly, it optimizes the travel time for your fast-moving items. In a U-flow, you slot your highest velocity SKUs right next to the dock doors.
Oh, I see. So they come off the inbound truck, get stored just a few aisles away, and when an order drops, they travel a very short distance right back out to the outbound truck.
Exactly. You completely avoid dragging your most popular items all the way across the entire footprint of the facility.
That makes so much sense. It's so elegant.
And it enables cross-docking, which is huge. Cross-docking is when you take products from an incoming truck, sort them in a central staging area, and immediately load them onto an outbound truck, bypassing the storage racks entirely.
Wow, skipping storage completely.
Yes. Because the inbound and outbound docks share the same staging area in a U-flow layout, a pallet can move from an arriving trailer to a departing trailer in minutes.
And in a through-flow layout, that same pallet would have to be driven all the way across the building just to bypass storage.
Exactly, which is just wasted time and fuel.
Okay, so the physical layout of the building dictates the macro flow, but the text also dives into the micro flow, how workers actually navigate the individual aisle.
Right, the granular routing.
Yeah. And you have the choice between conventional aisles, which give forklifts plenty of room to pass each other, or very narrow aisles, which the text notes can increase your storage capacity by up to 50%.
You gain massive capacity with those narrow aisles, but the trade-off is operational speed and, safety margins.
Because it's a tight squeeze.
Very tight, very narrow aisles require wire-guided or rail-guided equipment. A human driver simply cannot steer a forklift with an inch of clearance on either side without eventually destroying a rack.
Which would be catastrophic.
Yeah.
Okay, and once you've decided on the aisle width, you have to figure out how to route the picker through them. The text shows a diagram of an S-shaped picking route, where a worker just snakes up and down every single aisle sequentially.
Which is a very traditional method.
But if I need an item at the front of aisle 1 and an item at the front of aisle 3, an S-shaped route forces me to walk the entire length of aisle 2 just to get to the next item. That seems, wildly inefficient.
It is. Travel time often accounts for over half of the total time spent picking orders. Over half.
Wow. Just walking.
Just walking. If you rely on basic S-shaped routing, you are paying your labor force to walk miles of empty aisles. This is why optimal routing algorithms will utilize midpoint cross aisles.
Okay, what are those exactly?
They are essentially tunnels cut right through the middle of the storage racks, allowing a worker to cross over to the next aisle without walking all the way to the end of the building.
Oh, that is smart. Okay, so we've engineered this massive 14-meter-high cube. We've implemented a U-flow traffic pattern to prioritize fast movers and cross-docking, and we've cut cross-aisle tunnels to minimize walking distance.
That's a highly optimized physical layer, yeah.
But managing millions of SKUs, tracking inventory in real time, and routing workers optimally is just It's beyond human capability. We need a digital layer to orchestrate the physical layer.
Absolutely. You cannot run a modern warehouse on clipboards and radios.
Right. And the text outlines 3 distinct tiers of software: the WMS, the WES, and the WCS.
The software stack is what actually animates the building. The WMS, the warehouse management system, operates at the macro level. It manages the inbound orders, allocates the inventory to specific slots, generates the pick lists, and tracks stock levels.
Okay, so that's the big picture.
Right. Below that, you have the WES, the warehouse execution system, which handles the real-time coordination of labor and equipment. And then at the machine level, you have the WCS, the warehouse control system.
Okay, to keep these 3 straight, I was actually trying to map them onto an airport environment while I was reading. Tell me if this structural analogy holds up.
Sure, let's hear it.
So the WMS is the air traffic control tower. It has the radar, it knows the master schedule, and it dictates which flights are coming in and where they generally need to go.
Okay, yep.
Then the WES is the ground crew dispatcher. They're dealing with the real-time chaos on the tarmac. If a gate is suddenly blocked or a baggage cart breaks down, the WES pivots the staff and changes the routing instantly.
Yes, perfectly said.
And finally, the WCS is the autopilot software inside the actual plane. It's the system firing the electrical impulses to steer the flaps and physically move the machine.
That analogy tracks perfectly with how authority is delegated in the software stack. It really does. And if we connect this to the bigger picture, these systems are constantly communicating with the overarching ERP of the company.
The Enterprise Resource Planning System.
Exactly. When a customer clicks buy and an order drops into the ERP, the WMS acts as the air traffic controller, locating the specific item and scheduling the task.
But the warehouse floor is highly dynamic, right? Things change minute by minute.
Exactly. That's where the WES steps in as the dispatcher. It knows that, say, forklift driver A is currently on break, and aisle 4 is congested, so it dynamically assigns the task to picker B, who happens to already be nearby.
And then the WCS takes over the mechanical execution.
Exactly. The WCS takes the command from the WES and translates it into physical automation. It spins up the motor on a specific zone of a conveyor belt, or it calculates the exact coordinate path for an autonomous mobile robot.
It's just a continuous, instantaneous cascade from a high-level corporate order down to a tiny motor turning on a belt. That is fascinating.
It really is.
You know, the text also mentions the auto store system, which seems to take this digital control to an absolute extreme.
Oh, the auto store is incredible.
It's this modular cube grid, right, where robots just drive along the top of a massive hive of bins, pulling up inventory. So in that case, the WCS is essentially playing a flawless, high-speed game of traffic control, telling dozens of robots exactly when to stop and start so they don't crash into each other on the grid.
Exactly. It's pure mathematics in motion.
It's brilliant. But it brings up a critical operations question for me. If you build this highly optimized physical space and overlay it with a state-of-the-art software stack, how do you actually measure if it is working? I mean, how do you know you're not just moving boxes efficiently in the wrong direction?
That is the million-dollar question. You have to measure performance, and you have to measure it correctly. A very common operational trap is confusing utilization with efficiency.
Yes. The source material draws a very sharp distinction between these 2 metrics. And this stood out to me because people use those words interchangeably in business all the time.
All the time. But conceptually, they measure entirely different behaviors.
Right. So imagine a receiving crew waiting on the dock for an inbound truck that is, say, stuck in traffic. For 2 hours, they're just standing around. Their utilization metric drops because they are not actively working compared to the time they are on the clock, right?
Exactly. Their utilization is terrible in that moment.
But when the truck finally arrives, this crew is so experienced that they unload it twice as fast as the standard expectation. So their efficiency is through the roof, even though their utilization for the shift looks terrible.
That captures the dynamic perfectly. Utilization simply measures if a resource is busy. That's it. Efficiency measures output against a standard expectation. You cannot just measure if people are moving. You have to measure if they're actually producing results when they move.
This raises an important question, though, regarding human behavior. If I'm a floor manager and I only look at utilization, I could theoretically have a crew that is 100% utilized. They never take a break. They are walking nonstop for their entire shift, but they are highly inefficient because they are walking those terrible S-shaped routes instead of using the cross aisles.
Yes.
They're incredibly busy, but they aren't actually getting boxes out the door.
Which is exactly why relying on a single metric usually creates perverse incentives. If you just push the WMS to demand higher throughput and you only measure utilization, workers will cut corners to look busy.
Which leads to burnout and mistakes.
Exactly. This is why the text emphasizes balanced scorecard models like ScoreDS. You have to balance speed and cost metrics with reliability and, crucially, with health and safety metrics.
So keeping a holistic view.
Right. Because if your efficiency numbers look great, but your absenteeism and equipment damage rates are spiking, your system is actually failing. The human element is breaking down.
To combat that, the material dives into lean principles, specifically outlining the 5 C's to standardize the environment. But instead of just listing them out, let's look at how a couple of these actually change the physical reality of the floor. Take configure and conform. How does configuring a location plan actually affect a picker's day?
Well, configuring is really about macroergonomics and velocity. If you analyze the data and realize a specific component is picked 500 times a day, you don't just put it anywhere.
Right, you wouldn't hide it in the back.
Exactly. You configure the rack so that item is placed exactly at waist height near the front of the aisle. The worker doesn't have to reach up, they don't have to bend down, and they don't have to walk far.
It's all about minimizing friction.
Yes. You've shaved 3 seconds and a tiny amount of physical strain off a task that happens 500 times a shift. That adds up massively.
And then conform locks that gain into place, right? You create a standard operating procedure so that the next shift doesn't randomly decide to put that heavy, fast-moving item on the bottom rack where people have to strain their backs to get it.
Precisely. You establish the standard, and then you audit against it. You trace the documentation trail from the receiving dock all the way to shipping to ensure there are no hidden variances, because the software assumes the warehouse looks a certain way.
Oh, of course.
If the physical reality on the floor doesn't conform to the digital map in the WMS, the entire system breaks down. The robots and the humans get completely lost.
Wow. So what does this all mean for you listening? We started by talking about the hidden choreography behind global commerce. And what we've seen is that a warehouse isn't just a big room with boxes. It is essentially a giant, highly sensitive machine.
Very sensitive.
It requires a delicate balance of cubic space engineering, traffic flow optimization, deeply integrated software, and standardized human labor just to keep the supply chain moving without tearing itself apart.
It is a profound balancing act. And, I want to leave you with a final thought regarding those automated grid systems we discussed earlier, like the auto store.
Okay, yeah.
The text highlights how these automated storage and retrieval systems function without needing traditional human infrastructure. Think about that for a second. If autonomous robots are doing all the picking and sorting on a dense grid, they don't need 2.4-meter aisles.
Because they don't drive forklifts.
Right. They don't need overhead lighting.
Yeah.
They don't need oxygen or temperature control for human comfort.
Oh, wow. I hadn't even thought of that.
Yeah. So as this technology scales, the physical architecture of tomorrow's logistics networks will radically change.
Yeah.
We may see the rise of dark warehouses facilities buried entirely underground, or perhaps stacked into towering windowless obelisks right in the center of our cities, operating in total darkness because the constraints of human layout no longer apply.
That is an incredible image to end on. A windowless obelisk of pure automated efficiency just humming away in the dark. The next time a delivery truck pulls up to your door, take a second to think about the cubic math, the routing algorithms, and the digital systems that made it possible. Thank you for joining us on this deep dive. We'll catch you next time.